the supervision of Dr. D. Amarnath Reddy, Department of Sciences, TDM Kurnool. Today I will present a talk on fundamentals of supercapacitors and their application in modern energy storages. And this talk divided into 4 parts: introduction, working principle of supercapacitors, fabrication of nanoscale materials, and asymmetric device results and application. We all know energy is indispensable and essential for our life. Why? Because to function our body, biological functions, we need energy. And also we need lighting and communication, lighting, heating, communication, transportation. For manufacturing purpose, we need energy storage. Energy, not energy storage, energy. And the figure 1 depicts a typical all India daily load curve. You can see on average we are consuming 125 to 130 gigawatt energy in a day. That means it tells how much it is crucial for our lives. Generally there are 2 kinds of energy sources in nature, non-renewable energy sources and renewable energy sources. We are converting these energy sources into electricity. These are called as secondary energy sources. Actually these non-renewable and renewable sources are called as primary energy sources. We are deriving electricity from these sources only. And this is the present trends in electricity generation. You can see from 1985 to 2024 there is a gradual increase the utilization of renewable energy sources by generating to generate electricity. You can see 9,868 terawatt hour we are producing by using renewable energy sources. And also this is the electricity generation mix in various countries. For India, we are producing nearly 22% renewable energy based electricity. The major issue with renewable energy sources, they are suffering from intrinsic limitations. That means if you consider a solar energy with respect to location, with respect to time, there is a change in sunlight or sun intensity. We need to use energy storage. When the electricity is generated, we can use that is our demand. We can counter the problem of intermittency. We can ensure continuity by using energy storage device and restrict the wastage. And we are also using the energy storage in e-vehicles and ensure availability as per the need. We know the basic energy storages, batteries, supercapacitors and capacitors, and also fuel cells also there. These are various parameters: chemical energy and thermal energy, mechanical energy and electrical energy. In that we have chosen the supercapacitors. Why? Because the supercapacitors having 95% round trip efficiency. That means Coulombic efficiency.
Is it okay to ask questions in between?
And also this Rang-on plot gives an idea and importance of supercapacitors. The supercapacitors are bridges the gap between batteries and capacitors. Actually the capacitors having high power density which are applicable for high power applications. But in the case of batteries which stores huge amount of energy, that means energy density is more, but the releasing capacity is less compared to the capacitors. The capacitors are bridges the gap between these two. That means the capacitors having moderate energy density and power density. The work is going on to increase the energy density of supercapacitor. The major issue with the supercapacitors is they are suffered from low energy density. These are some few advantages of supercapacitors: high capacitance, fast charging ability.
What is the difference between power density and energy density?
Some equipment needs sudden release of output. For suppose if you consider a fan, the fan having the condenser, that is nothing but a capacitor. Initially, when you switch on the power, it stores the energy and it suddenly releases. That's why it is rotating. Initially, it needs initial thrust. And also in vehicles also self motor needs capacitors. In that case, high release of amount we need. That's why they are using Conventional capacitors.
My question is power density and energy density. Energy density, we know that.
Energy density is nothing but storage. Power density means releasing, output. Major issue, low energy density. You can clearly understand. Here, two persons. One person is expert in 100 meters and one person is marathon. In marathon, he uses the energy, entire energy for a long period. But in the 100 meters, he uses that entire energy in short period. That means supercapacitors. It is in a batteries. And this is another example. Power density and energy density. It will deliver, supercapacitor deliver entire amount in a short period of time. Here the battery delivers entire energy in the long period of time. These are some examples and applications. Supercapacitors are used in aircrafts also. For emergency purpose, we need to open the doors in immediately. At that purpose, they are using supercapacitors. This is the one of the largest passenger plane in European aircrafts. Nearly which accommodate 850 passengers. Regenerative braking system also we are using the supercapacitor in the place of batteries. Why? Because it is very short period to charge.
What is the charging time in general like?
30 seconds.
30
I will
seconds.
show. China is using electric buses. Each and every bus stop there is a charging point. Within 30 to 50 seconds it will charge. And also that charging is used up to 7 miles. After 7 miles it will again charge. Each stop there is a charging point. Generally, this is the working principle of supercapacitor. It contains two phenomena: electric double layer and redox pseudocapacitance. Electric double layer means the accumulation of electrolyte ions on the surface of the electrode. That means EDLC. Here there is a chemical reaction. That one is a physical phenomena. That means their accumulation. Here the chemical reaction. There is a redox reactions in the pseudocapacitance. Based on mechanism, these are classified into three types: EDLC, pseudocapacitor, and hybrid type. EDLC means Faradic, non-Faradic type. This one Faradic type, where redox reactions happens. That capacitors are called pseudocapacitors. By combining EDLC and pseudocapacitor, we are producing hybrid capacitors, which exhibit both reactions, Faradic and non-Faradic. The major issue is energy density is still less. We need to increase. How to increase? By using this fundamental equation, E equal to half CV square. We can increase energy density by either increase C or V. C means capacity of the electrode, V means total potential window of the device. There are some ways to increase capacity and voltage. You can increase the specific surface area of the electrode material. Then only that electrode accumulate more number of ions on the surface of the electrode. And also electrical conductivity. Some materials having less electrical conductivity, some materials have high conductivity. We need high conductive materials. And also additional redox capacitance. We need to add 2 more materials. That means we need to increase the oxidation states of the material. If more number of oxidation states are there, multi-metal is there, we will get more number of reactions. How to increase the potential? By using organic electrolyte ionic liquids. And also asymmetric supercapacitor means we are fabricating 2 different types materials. Anode is made with one material and cathode is made with one material. By combining both materials, we will get increasing potential window. One is at 0 to 1, one is at 0 to 0.5 potential. We combining, we will get 1.5 volt. If you take symmetrical, both having same material, which produce only 0.5. For suppose one is 0.5, one is 0.5. By combining only 0.5. if you take asymmetric device, we are evaluating the electrochemical reactions from 0 to -1 for anode. For cathode, we are evaluating 0 to 0.5. That's why the total difference is 1.5. This is the progress of my literature survey, problem identification. These are all no. Yeah. So many DC meetings were there. After literature survey, we chosen that metal sulfides. We fabricated. In the project one, we fabricated multi-metal sulfides by hydrothermal method. After that, we incorporated these structures into the high conductive materials like titanium carbide. Then only we will get a high conductive device. In this project, we get nearly 20.4 watt-hour per kg energy density. This is the diagram represents the asymmetric supercapacitor. Positive and negative. Negative is fabricated with activated electrode, and positive is metal sulfide. These are the various.
Just go back now. That
Ah.
FSM images are they rods
These
and
one.
thing?
These
Are those images? They are
These
wires.
are software.
No. That SEM image.
This one's MMS.
So it's like a rod kind of thing or wire
The
or some
here the
plastic.
nanorods are self-assembled and forms the micro rods.
Micro rod. What are the
Actually here single nanorods are combined in the hydrothermal process. At that process we get the micro rods, micro to submicro. And calculating that average thickness of the each rod, we got notice that are micro to submicro rods.
Here in this square, there are some 5 dots are there. Those are 5 different samples.
No. These are at different current densities. 1 ampere per gram, 2 ampere per gram, 4 ampere per gram. Initially we are giving a charge at constant current. Each constant current we are calculated the energy density.
Then what are the other dots like?
These are at 1 ampere per gram.
Then in your case?
Here 1, 2, 3, 4 and 10.
So the first one is comparable to other.
Comparable to previous lectures.
Then that other 4 we cannot compare. And what is the software you used for this image and all?
This one, this
Like
one, the Korea people they did.
And previously also. Image is for data or that image also.
PPT. This one only Korea people.
PPT.
This one PPT. All PPT.
This density, the graph.
These are all PPT.
Sir, that energy density.
Versus power density.
And this MXC you guys purchased now. MXC? How much is the cost?
Actually, they purchased max phase.
Max space.
Max phase they purchased less quantity. From the max phase means titanium carbide is combined with aluminum. Aluminum is there in max phase. We need to remove that aluminum from that max phase. We will get the few layered trees.
You have removed it.
They from that we purchase.
And how much is the cost?
Max phase nearly 1 gram 6,000 and 7,000. If you purchase directly that few layer mixing, that is very costly, 20,000.
For preparation of your sample, for suppose you are preparing today, how much minimum quantity you need?
1 mg, 2 mg.
That is sufficient.
If you take bulk amount of mixing, the
Agglomeration.
that means the layers will automatically stack.
You optimize to that amount or optimize?
Up to 3 mg, we are getting good results. Greater than 3 mg, there is a stacking. In XRD also, we are getting the mixing peak. Up to 3 mg, we don't notice that mixing peak. These are some videos. In the second project, we synthesized again multi-metal sulfides by using metal organic frameworks. Same synthesis. First we derived ZF67. From that ZF67, we fabricated single shell structures. From that single shell, we derived double shell structures. From that double shell, we derived multi-metal sulfide nanostructures.
You have right age for 24
24 hours.
Why age? I have the same doubt. That's what I didn't get that.
The precipitation formed at the 24 hours. After mixing, that
Immediately it did it.
Incident రాసింది
To complete the reaction.
to complete
సెకండ్ ఆర్ ఫస్ట్
This is not hydrothermal, this is co-precipitation.
that's it. Same characterizations, same test.
సార్ చెప్పండి ఇది టెక్నికల్ టాక్ జరుగుతుంది తుంగభద్ర సంఘాలలో ఒక పావు గంటలో వస్తాం